So today we're looking at the quotient rule. And remember how the sum and difference rule was so obvious that you could just take the derivative of each thing separately and add them up? And then we thought with the product rule, wouldn't it be nice if we could just take the derivative of each thing separate and multiply? And we found out that didn't work. And the product rule is a little bit more advanced. Well, the quotient rule gets even worse. So here's the quotient rule. What it says is if you have one function divided by another function, what's the derivative going to be? Well, you're going to keep your bottom one the same and multiply it by the derivative of the top one. Then you're going to keep your top one the same and multiply it by the derivative of the bottom one. And so it's very similar to the product rule that way, but now we're going to be subtracting instead of adding. And then finally, you're going to divide by the bottom one and then square it. That's in one notation. You can take out this because you don't get a formula sheet, sorry. So you can white that out. And here it's the same idea. We have one function on top, one function on the bottom. Then you keep the bottom one the same, multiplied derivative of the top one, minus the top one the same, multiplied by the derivative of the bottom one, finally divided by the bottom one squared. So you can see when we color code it, both of those formulas mean the same thing, they're just in different notations. It's whether we use the notations of the derivative by saying u prime, or if we use du dx. Yes? No, they're both identical. It's just a matter of how you like to write your derivatives. And on a test, for the most part, you never write down the actual formula. You usually just go into the process of doing the derivative. So these formulas you'll have to have memorized, but you'll have to know how to use them. So how do we use these formulas? Well, let's look at some questions where we can find the derivative. So remember the d dx out in front means find the derivative of, and here we have a function on top divided by another function. So we have x cubed divided by 3x minus 7. So we keep the bottom one the same, 3x minus 7, and multiply it by the derivative of the top one. The derivative of x cubed will be 3x squared, minus keep the top one the same, and multiply by the derivative of the bottom one, all divided by the bottom one squared. So this is just plugging things into the formula, color coding again just to see what's happened. We have kept the bottom one the same here, and then derivative of the top one. Then we kept the top one the same here, multiplied by the derivative of the bottom one. And then on the bottom, we're left with the bottom one all squared. Now, when you go to do the homework in this section, you'll notice that your answer key often writes your final answer in factored form. So what they're going to look at is they're going to look at the top and say, is there anything you can factor out of the top? And if you can factor that out of the top, is there anything you could simplify? So in this case, can you see that there's a 3x squared in both the first and the second term as a common factor? So we can take that out. I'll use square brackets here. We'll be left with 3x minus 7 minus, and here we'd be left with just an x. Once we factored it out, we might realize I can simplify this a little bit. Inside the brackets here, 3x minus x will give me 2x minus 7 2x minus 7 and 3x minus 7 are very close. Can we simplify that? No. So this would be as far as you could go, and most likely your answer key in your textbook will have it in a simplified factored form like this. It's nice to be able to factor it because now we can easily tell of the derivatives here, where is this equal to 0? Well, a fraction is equal to 0 whenever the numerator is equal to 0. So can you see that when x is 0, the whole numerator would equal 0? Can you see that when x is 7 halves, or 3.5, then this set of brackets here would equal 0? And that's going to come up important as we move later on. We're going to want to try to find out where are derivatives equal to 0, because that's where the slope of the tangent is completely horizontal. And as far as graphs go, that will always happen when a graph either has a maximum point or a minimum point. So we'll see that as being important later on. Yes. We're going to be using, in our next unit, we're going to be using our calculus to graph all sorts of functions we couldn't graph before. So here we have another function. We have a function on top, a function on the bottom. I'll get you to try to plug this one into your formula to see how you do, and then we'll look at trying to simplify it. All right. How did you do? So again, if we color code things here, we have our function on our top, function on our bottom. We start with our function on the bottom right here. We have our function on the top right here, and our function on the bottom right there. What's not highlighted is always the derivative of the other function. Yes? Well, looking at this one, and I look at my first term and my last term, I don't see any common factor. Okay, so sometimes it's going to jump out that there is a common factor. In this case, there isn't. So this one is one of the examples where we would leave it like this, because there's nothing really we could do to simplify easily. You could multiply these first two out and multiply the last ones out, combine like terms, and then try to factor whatever you get. But looking at this, can you see that you're going to get an x to the 5? And that's not going to be fun to factor. You could use your factor theorem and remainder theorem to try, but it's going to take a long time, and so it's not going to be something that's going to be easy to do or quick to do. But you may find in your answer key they will have multiplied it out and at least combined the like terms. So again, once you're doing your homework in this section, it's really important that you do have your answer key open, and once you've done step 1, then it sort of turns into like a mini proof. Look at the answer key. Can you manipulate your equation to look like that? Can you get your algebra skills to do that? Because that's going to be really helpful. What does the word gradient mean again? It's another word for slope. Woo. It's an ugly L. So gradient is another word for slope. Remember, our derivative tells us the slope of every single tangent line possible at every single x point. So if we've got this equation, if we find the derivative will tell us the formula for finding the slope at any x value we like. In fact, our derivative is a function of slopes of every single tangent line. So we want to find the slope of that at x equals -1. In order to do that, if we find our derivative, we're going to find out all the slopes. And then if we plug in -1, we're going to find out that specific slope. Again, we have a quotient here, so we'll go to our quotient rule, keep the bottom one the same, derivative of the top, keep the top the same, derivative of the bottom, all over the bottom squared. at this point, if we want to find the slope of the tangent at x equals -1, we can plug in -1 for x. So our slope will equal -1 squared plus 1, 3 times -1 squared minus -1 cubed, 2 times -1. So I just plugged in a -1 in brackets wherever there was an x. We're going to get 1 plus 1, that'll be 2. -1 squared is a positive 1 times the 3 will be 3. -1 cubed will be -1. 2 times -1 will be -2. All over 1 plus 1 will be 2 squared. Here we're going to get 6 minus 2, which will be 4 over 4. So all that work to find out the slope is equal to 1. Now that we have the slope of our line, notice the question was asking us to find the equation of the tangent line at x equals -1. In order to find an equation, you always need the slope, which we just found out was 1, and a point. And the point is -1 comma, does it give us the y value? No. So how do we find the y value of that point? We'd plug in -1 into our original function, because we're trying to find a slope of a tangent to a point on that original graph. So if I plug in -1 into x cubed over x squared plus 1, can you see that you're going to get -1 over 2 as our point? So then in order to find our equation of our line, either you'll use y equals mx plus b, or the point slope form, whichever you remember best and find easiest. So how to use y equals mx plus b? Well, we know the slope is 1, and we know a point when x is -1, y is a half. And once you plug that in, the only thing you don't have is b. Add 1 to both sides, and you'll get b is 3/2. So our equation is y equals x plus 3/2. Oh, y is -1/2? Thank you. So then when I add 1 to both sides, I will get 1/2. Thank you. X plus 1/2. In the point slope formula, again, you plug in 1 for your slope, and you plug in your point for y1 and x1. Plugging in our point, we'll get y plus 1/2 equals x plus 1. Subtract 1/2 on both sides. And we get the same equation either way. So whichever one you're more comfortable with to help you find the equation of the line. So what we did when we find our derivative right here, this is sometimes called a slope function or a gradient function, because the derivative is telling you the slope of every single tangent line that's possible. We were concerned only with the one at x equals -1. So in that case, we plug in -1 and we get the slope of ours right at that point. Once we have that, we have a point by plugging it into the original function, and we can find our equation of our tangent line from that. All right, so what the program is doing here is as I move this tangent along, it's plotting every single slope. And as it plots all those slopes, it makes that crazy blue graph. That blue graph that we see right there is the equation for that blue graph. No, wrong one. Equation for that blue graph is our derivative here. So if you wanted to graph what we found out here as our derivative, it looks like that blue function. Now if we slide this point until we get to -1, as close as we can, whoa, see, and over on the left where it says derivative, it says the point, so you see how close I'm getting to -1? Oh. I'm sure there's a way I can get it exact, but this is way more fun. 0.99? Maybe if I zoom in, I can do better. Yes! So, there we go. I got it right at -1, and it tells me the slope of that line is 1. And I also had this program create the equation of that tangent line. So in the red here, you see that it is x plus 0.5, which is what we found as well. Okay. All right, let's see how you did. So first, we find the derivative. That first line there is just using the quotient rule. Then if you want it to match, notice that your denominator already matches. You wanted an x plus 2 squared on the bottom, you've got an x plus 2 squared on the bottom. But on the top, it doesn't quite match, so you say, what could I do algebraically to manipulate this? Here it makes sense to multiply things out. Remember, when you're subtracting an entire function, you're subtracting each term, so that's why all the signs change there. Combine your like terms, and sure enough, it matches up. I don't know if you've seen an end of a proof with QED. Sometimes at the end of a proof, textbooks will write QED. It's short form for Latin, which I don't know exactly the Latin, but it's something like quod erat demonstratum, which means what was asked for has been shown or demonstrated. So it's sort of like a fancy way to say I've shown what you wanted me to show. And it's a nice way to say I'm done. I've proven what I want. Now the second part of the question asked, when is the derivative undefined? When is this not possible? This is not possible when x is equal to -2. Because if x is equal to -2, you would be dividing by 0. So you have some homework questions to try at the end. We're going to take the rest of class to work on those. Again, make sure you have your answer key open so that you know how to manipulate to make things match up.